So let's get started with the first part, where we look at the frequencies of characters in the text. And to start off, I want to talk about character encodings, which is an even more fundamental question. In a computer memory, we have to encode strings by binary sequence of bits. So we have to somehow specify how characters are mapped to bits. The simplest form of encoding is that each character in the source text is just individually mapped to some sequence of strings. Now, a bit more of terminology. We will use E as a function that maps a single character to its code word. So the bit string that represents a single character from the source alphabet. Because usually the source alphabet is not binary, but contains many more characters, we will need several characters to represent, several bits to represent a single character. And we will write this sequence of bits as E of C. And code word reflects this fact that it's a whole word of bits, not just a single bit. There will be two main types of character encodings. They can either be fixed length codes, in which for all characters in our source alphabet, sorry, this should be S, all characters in the source alphabet are encoded with a code word of the same length. Those are the simplest types of codes, but they're also widely used, and because they're simple, they make processing of the strings faster. But there's also the option that the code words have different lengths, and then it's called a variable length code. Let's look at a very famous fixed length code. That's the ASCII encoding, the American Standard Code for Information Interchange from 1963. So it's quite dated, and well, like it's often the case with American standards, they don't care very much for languages other than English. So if you look at the characters you can represent in ASCII, it's the Latin characters in upper and lower case, a couple of other symbols and punctuation marks, plus these control characters that come from the early history of line printers, and they don't even have a real meaning. Many of them don't even have a real meaning in today's text files. But that's what ASCII is to date. So it uses 7 bits for a single character. It has 128 different characters that it can encode. And not all of them are actually characters in the classical sense that you can write them down. The benefit of a fixed length code, as I said before, is the encoding and decoding is as fast as it gets. You simply have to jump to the right position in your bit string to start decoding, or encoding is just as easy. In terms of a compression method, this is not very effective, because only when all the characters are equally likely, if they occur with the same frequency, will this be effective. But for most cases, you hopefully assume that E will occur much more often than the AC control code, or whatever all those other weird things mean. So you won't usually have equally distributed characters, and in that case, this encoding wastes space. The other problem I alluded to is it's not flexible, in the sense that you don't even have the simplest diacritics or other characters that appear in other European and languages that don't even use the Latin alphabet. So how to represent a character that's not in this originally thought of alphabet, it's just plain impossible. On the other hand, variable length codes can solve this problem And I put this on the slide to show you that this is not at all a novel invention. Variable length codes are around for quite a while. And Morse code might not even be the oldest example, but it's one. So we allow more flexibility by having different lengths for the code words. And well, in case you've never seen Morse code, this is a character is represented by a sequence of dots and dashes. And the dot is a short map, and the dash is a long map, and you have the spaces in between. There's a precise definition that's given here, what you how you should translate this into, well, signals on and off. For encoding, you would use a table like this, where you find the characters in alphabetic order, and then it's easy to find, for example, the code for S, 3 short dots, then O, 3 long, and then 3 short again, SOS, the famous emergency code. If you want to decode, if you send a sequence of shorts and longs, you would rather like to use this try style dictionary. So this is for encoding, and this really is for decoding. Then if you receive short, 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 you would go short, 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 and you see S. If you then receive long, 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 O, and S again. That's how you can decode Morse code. And it's a variable length code because it's obvious that not all characters are represented with the same number of symbols. There's another very widespread variable length code that I'm sure you use all the time, maybe without noticing, and probably without realizing that it's a variable length code to begin with. And that's UTF-8. It's part of the Unicode standard, and it's a way to represent any Unicode character, including the fanciest new emoji for lobster or whatever. But still, it uses only a single byte for a character if you stay within the old ASCII characters. So the trick how it works is that it uses between 1 and 4 bytes, so 8 up to 32 bits for each single character. And this can be, so the characters that are represented with a single byte, they start with a 0 to indicate this. And then comes the code, the 7 bits for the ASCII character. And for the other characters that are not part of ASCII, but part of the much larger Unicode standard, which has 140,000 characters by now, you would need several bytes. And how you can do this is shown in this table. So the details of this are not relevant. I included them just in case you're curious how UTF-8 actually works. I left this in. The details are not part of the material for this class, but I think it's important to know that UTF-8 really is a variable length code. And then again, it's a kind of compression scheme because you can represent all the Unicode characters, of which there are quite a lot. But if you stay with standard English prose, most characters will only require the 8 bits, which is much less than what you would need to represent all those with a fixed length code. So in a sense, it's a compression scheme, even though it's not very space efficient. Okay, let's try to get a little more systematic about what a code is and maybe what is not a code. We could have a small alphabet, just those 4 characters, A, N, B, and S. And you can just assign some code words to this. Then if we have a text over this alphabet, we can encode this. We look up the code for B, that's 001. We can look up the code for A, that's 0. We can look up the code for N, that's 10, and so on. So you just concatenate the code words for the individual characters. And that gives you the code for banana. Now let's do a quick experiment if you're still here. Let me hear if you think there is a problem in this code or not in the live chat. So just post a yes or no. There's a problem or no problem. Everyone's sleeping. Aha. Okay, one answer was, I'm not sure if the code is unique. Okay, some more think there's problems. Okay, the answers come a little delayed. Very good. So people are still paying attention. That's good. I'm still trying to find a more effective way to get some instant feedback about the pace of the class. You're very right. This code has a problem. For example, the same code word can also be decoded to bass, and maybe even to other codes. I didn't check. But it's definitely a problematic code because it decodes to two things. Come on, that's bad. So it's not a valid code. We don't want these types of codes. How should we have known? Well, there's some hints in the chat about this. To be systematic about this, the problem comes from the fact, at least one problem comes from the fact that the code word for n, 0, 1, is a prefix of the code for another character, namely s. And that means whenever the decoder sees a code 0, 1, it has to guess whether it has to stop and report an n or continue reading and report an s if there was a 0. Now, if you have the code 101, you might say, okay, I'm fine. I know this cannot be an s, but it's in general a bit hard to figure out what it is. So we don't like these kind of codes that have this property, so let's just forbid them. We will only look at prefix-free codes, which is exactly the negation of this. No code word is a prefix of another code word. If a code is prefix-free, it's instantaneously decodable in the sense that whenever I read a piece of the text and that matches a code word, I can instantaneously claim in the source text there's the character that's represented by this code word, and I don't have to continue reading to figure out what this meant. And that's a good code. These are the codes that we like. Now, if you only consider prefix-free codes, that tells you something about how the code words can look like. And to give away this insight, a code is prefix-free if and only if we can draw it as a trie like this, so that the characters only appear in the leaves. So again, we take the code words and build a standard trie. So we're not trying to be space efficient for this trie. So it's not about compact tries or suffix trees or anything like that. Just the standard trie. So maybe something to note. The standard trie of code words. If you build this and it works, that means it was prefix-free. If you remember, when we were talking about tries, that was actually a condition that the strings we insert are prefix-free, because that meant every string will be represented by a leaf of its own. Now, one way to achieve prefix freeness is to append an end-of-word character. We could do this for our codes, but then we would need another character. So here what we really do is instead just make sure that the code words we pick happen to be prefix-free. So that's why we can avoid the dollar here. And well, just as an example, how would we encode an and with this code? Well, encoding again uses this table. So you would take the code for A, that's 10, then the code for N, 001, the code for space, 000, and so on and so forth. You just concatenate all those codes. And to decode, you would take the trie. You would read in the trie 1, 1. the first two ones give me a T, and I reach the leaf, so I'm sure I'm done. Then I start at the root again with the next character, which is another 1, then 0. 1, 0, and another 0. That gives you the O. Then you start again, 0, 0, 0, space. And you continue like this. All right. And so here you see the result. So that's the idea of code tries. And the nice property is, if a code is prefix free, then it has a code try of this shape, and any code try represents a prefix free code. So these are exactly the types of codes that we like. Now here's a little nitpick that I want to discuss right at the beginning of this unit. Sometimes it's not so clear if the used code is part of the message that we have to store or not. And that's really the distinction between fixed coding and the rest. So fixed coding means outside of the current communication, we agree that we will use the Morse code or we will use UTF-8. And then you don't have to store the code itself because the other person already knows that code. It's a fixed code that you build once and you use all the time. Now for file encodings, if you've ever had this gibberish of letters showing up in the wrong way, you know that if you have such a convention and people misinterpret the convention and use a different character encoding, things can get weird and they just decode the text incorrectly. This can happen if you use fixed coding and people don't follow the same convention. But UTF-8 has made this much better. The alternative is that in those two cases, we do transmit the code itself as part of the message. So we do not have to fix the code itself, we just have to fix a meta model of the code. What type of code and how the code is stored. That has to be fixed, but then the code itself might be more flexible. And there's the case of static coding, where the code depends on the message, but it stays the same throughout the message. We'll see an example of that just in the next subsection. And the other alternative is adaptive coding. That's a weird thing because the code itself changes while we are coding and decoding. That's a weird thing, but as you'll see in the example that we discuss later next week, I guess, you'll see that's a fairly natural thing in the applications where it actually occurs. But in those two cases, we have to transmit or store the code itself too. So if we compute the compression ratio, we should actually take the size of the code into account for these two.